Good evening, everyone. What we're going to be doing today is we're going to be converting mass into energy. So, this is probably one of the most famous equations in physics, which is the E equals mc squared, that Einstein equation. So, what we want to do is try to understand the relationship between energy and mass. So if we look at the nucleus, we have these positively charged atoms in the center where most of the mass is generated. And we also have these strong forces basically holding this nucleus together. So what we can do is we can actually convert that mass into energy, basically annihilate that nucleus and convert all that mass into straight up energy. We already spoke about the actual size of the nucleus. This nucleus is extremely tiny. It's compared to the atom size itself. So if again you made a full scale model, but instead of using baseball terms, we used football terms, it would basically be roughly of putting basically P in on the 50-yard line, and then basically the outer perimeter of the football stadium would be where the electron is. Everything else would be complete empty space. So now we have an energy mass relationship where we are going to completely and utterly simplify it. Now, what we do is we have this thing called the universal mass unit. This is where you get your atomic numbers from on your periodic table. So what we did was we found out carbon, we made that our gold standard. And we did was we grabbed carbon 12 and we divided that by 12, the mass of it, and we found one atomic mass unit. From that atomic mass unit, that's what the rough equivalent of a proton is going to be, and that is the rough equivalent of one neutron. Both of them are off by a little bit. One's a little bit bigger than the other, but that's going to be our rough standard. Is basically going to be our universal mass unit as say 1U. Okay. Now, one of the reasons why this completely simplifies this, instead of using the whole E equals mc squared equation, which we'll use right after, what they just did was they used that whole electron volt principle. Again, the electron volts came around to make life easier on us whenever we dealt with energy levels. So on your reference table on the front page, it actually shows this equality where you can convert one atomic mass unit into 9.31 times 10 to the second mega electron volts. So that's 931 mega electron volts. So remember, the mega is times 10 to the 6. So that's 931 with 6 zeros after it. That is a tremendous amount of energy. So even from one little proton being annihilated, you're going to get a huge amount of raw energy out of it. So Einstein basically saw this and tried finding the relationship with things besides electron volts, something that the scientific community commonly uses. So what he wanted to do was he wanted to find his energy in joules, which a lot of people use all the joules for energy values, for ionization energy, etc. So what he came up with and he found a relationship with was the energy that's being released from 1 kilogram of material is equivalent to that mass times the speed of light squared. So if you notice, if you get 1 kilogram, you are then multiplying it by 3 times 10 to the 8 squared. So that becomes 9 times 10 to the 16. So 1 kilogram of mass produces 9 times 10 to the 16 joules of energy. That's unbelievable. So when we think about things like our basically nuclear facilities, with the most minimal amount of nuclear material, we can produce tremendous amount of energy there. So if you look at it here, how much energy would be released if you had 12 atomic mass units? That's basically saying you have 12 protons or 12 neutrons. How much energy would be created? So what we would do is we would just do the basic conversion. Again, one atomic mass unit is equal to 9.3 times 10 to the 2 mega electron volts. We cross multiply and we get 11,000 mega electron volts, a tremendous amount of energy from just 12 protons. Now, if you want to look at it in terms of typical energy sources like joules, you want to look at how much energy would be generated if 2 kilograms of mass were completely converted into energy. Now, just to give you a perspective, the nuclear weapons that were produced and released on Japan had about 2 to 5 kilograms in them. And you saw how much devastation that caused. It's also good to know that not only was that 2 kilograms, that was 2 kilograms where only a fraction of it, a small fraction of it, actually detonated. So it didn't even detonate a full 2 kilograms. And that caused a tremendous amount of devastation. So if we look here, all we would do is we would plug it into the typical E equals mc squared equation. And you have 1.8 times 10 to the 17 joules of energy. That is tremendous. I mean, when we were talking about, like, say, a horsepower is 720 watts. So it's basically 720 joules per second. You're talking about 720. This is something, and that's a 1 horsepower engine. You want to talk about a supercar, which has 1,000 horsepower. That would be something like, a thousand joules every, say basically 720,000 joules every second. This is 1.8 with 17 zeros after it. It dwarfs that amount of energy. And that's why the nuclear energy is just so much more potent than chemical energy. And then last but not least, you could obviously go the other way. Instead of having how much energy do you get from mass, you could say how much mass would be required to generate this much energy. And this is kind of what you do with a nuclear reactor. You basically find out how much energy your system needs, your neighborhood. And what you would do is you would have a specific amount of material in that reactor to create this amount of energy that's produced for your environment. So all you would do is, again, E equals mc squared. Your energy would be in joules. Again, if you got your energy in mega electron volts, it would then convert to atomic mass units. So you only have joules that are coordinating with kilograms, and mega electron volts, those coordinate with your atomic mass units of U. Hope you enjoyed the video. Be safe.